Okay, so welcome back to section 6.4. We finished section 6.3 last one. Now it's time for 6.4. In section 6.3, we took a look at the idea of using sample data, sample statistics, to predict population parameters. And I said there's math that does this, there's math that does this, there's math that does this. Here's where the math comes into play. Now, one thing to keep in mind is when we are sampling to get our sample statistics, we are sampling with replacement. And there's two very important reasons why we do this. One, the samples are usually relatively small compared to the population. It makes no really significant difference whether we do or do not use replacement. But when you sample with replacement, the math is better, easier calculations and formulas. So we're assuming that the sampling that we're doing from the population is sampling with replacement, not without replacement. Without replacement creates a dependent relationship between the samples, which makes the math much harder. Okay. All right, so having gotten that out of the way, the central limit theorem. That is the title of section 6.4. And what the central limit theorem does is the central limit theorem allows us to use the normal distribution to make some very important and meaningful calculations and applications. The central limit theorem is the mathematical theorem that connects samples to populations. Right? And for us, we're going to start by talking about sample means and how they are connected to the central limit theorem. And the central limit theorem tells us that if we take all samples of size n, where n is sufficiently large, and our definition of large enough is 30, or, now here's an or. Ugh, I hate ors. Ors give us two scenarios where this is true. One, the first scenario is where we have sample sizes that are big enough. The second scenario is if the original distribution was normal, then we don't really care how big our sample is. But if your sample is large enough or the original population was normally distributed that you were sampling from, then we can use X bar to approximate a normal distribution, the sampling distribution of X bar, where our normal distribution has a mean, which is the population mean, and a standard deviation, which is the population standard deviation divided by the square root of the sample size. Wait, what? Let's lay it out step by step. If you sample from a population and you sample big enough or appropriately, then the mean of all your sample means is the mean of the population. The mean of the sample means, the mu sub x bar, the mean of the sample means, is the mean of the population. The standard deviation of the values is going to be the standard deviation of the population divided by the square root of the sample size. This is also sometimes referred to as the standard error of the mean, or sometimes the standard error on the mean. It goes by a couple different names. Okay. If, for whatever reason, you wanted to do some z-score conversions, you can still use that z-score formula. You just got to make sure that you convert the standard deviation in the denominator to that standard error on the mean. Okay. If your original population is not normal or your sample size is too small, we can't do it with the techniques in this course. There are ways to deal with that scenario outside the scope of this course. All right. In the problems we're going to be doing, we are going to start by checking our requirements. That is to check to make sure that we are sampling properly, either from a normal distribution or a large enough sample, and then calculate the sample means, the mean of the sample means, and the standard error on the mean correctly. Okay. Questions you need to keep a track of is the mean that is stated an individual value or a mean from a sample? Are you talking about an X bar? Are you talking about a mu? Are you talking about a mu sub X bar? What is it we're talking about the mean of? And when there's a reference to a standard deviation, is it a population standard deviation? Is it a sampling distribution, standard deviation? What are we being given in the problem? Let's look at what a problem looks like, and maybe we can make this make a little more sense, because this is kind of all over the place right now. Here's our problem. The elevator in the car rental building at the San Francisco International Airport has a placard stating that the maximum capacity is 4,000 pounds or 27 passengers. This converts to a mean passenger weight of about 148 pounds when the elevator is full. So if you take the 4,000 divided by 27, 148. We will assume the worst case scenario in which the elevator is filled with all 27 passengers, all of which happen to be male. Assume adult males have weights that are normally distributed with a mean of 189 pounds and a standard deviation of 39 pounds. Right? Now we're going to be asked to calculate some probabilities. So all of this is set up, right? All of this is a setup for the problem. There's some information in here. I know that adult males have weights that are normally distributed. I'm told that they have a mean of 189 pounds. So since we're talking about a normal distribution, I know that we have a mu of 189. And I'm also told that I have a standard deviation of 39. So since we're talking about a population there, I know that that's going to be a sigma of 39, right? And the first thing that they're asked to do here, the first calculation we're asked to make, is to find the probability that one randomly selected adult male has a weight greater than 148 pounds. Okay, well, let's see. I'm told that men are normally distributed with a mean of 189, a standard deviation of 39, and we want to find the probability that they weigh more than 148. So we want this right tail. So we're finding the probability that X is greater than 148 pounds. Okay, I want to point out something. You see how I wrote X there? Because I'm asking to find the probability of one single randomly selected individual. Now the math that I do here is the same math that I've done before. Grab my calculator, go to my distribution menu, normal CDF. I have a lower limit of 148. I have no upper limit, so big number. I have a mean of 189. I have a standard deviation of 39. And I see that this is about a 8534.8534, or that we have about an 85.34% chance of a randomly selected individual having a weight that is greater than 148 pounds. Okay, now let's take a look at how the question changes when we go from talking about a single individual in a population to a sample from a population. The second part asks, find the probability that a sample of 27 randomly selected adult males has a mean weight greater than 148. Well, this part's the same. That's the same. Has a mean weight greater, has a mean weight greater. Wait, no, it's not. Up here, it just says has a weight greater. This says has a mean weight, right? So they want us to perform a probability calculation on a sampling distribution. Well, before I can perform a probability calculation on a sampling distribution, I have to make sure that it meets the requirements. Is my sample large enough? Well, large enough would be that n was greater than 30, and we're only sampling 27, so that's not true. But there was an or in that. It was either it's enough or the original population was normally distributed, and we were told that men's weights are normally distributed, so the fact that it's too small is okay for this problem. So then we're going to find that probability. Now the central limit theorem tells me that the distribution of our sample means is going to be normally distributed, and the mean of the sample means will be the same as the mean of the population at 189. It also tells me that the standard deviation for a sample from a population will be the standard deviation of the population divided by the square root of the sample size, which in this case is going to be 39 divided by the square root of 27. I don't care what that number works out to be. I'll worry about that later. And now they want us to put 148 over here. And they want us to calculate the probability that a sample mean will be greater than 148. Now I want to point out a huge difference right here. In the previous example, when I put an X there, I'm talking about one from a population. When I put an X bar there, I'm talking about a sample from a population. So I'm finding the probability that a sample has an average of 148 or more. Now the math that I do is the same. I'm going to grab my calculator. I'm going to go to my distribution menu. I'm going to do a normal CDF. I have a lower limit of 148. I don't have an upper limit because it's a right tail problem, so I'm just going to go to forever. My mean is still the same, but my standard deviation is now going to change. My standard deviation is going to be 39 divided by the square root of 27. I'm going to paste that back in, and I get, well, 0.99999. That's essentially 1, right? No matter how I slice that and round it, I'm getting a probability of 1, or roughly 100%. So what does that tell me? Well, mathematically, it tells me it's almost guaranteed that the average, the mean weight, will be 148 or more. More importantly, it's telling me that if I put 27 guys in this elevator, there's very little chance I'm going to meet that weight. There's like 100% chance that I'm going to exceed the weight restrictions on that elevator. That's what that's telling me. That scares me a little bit. I don't like elevators in general, and I don't like crowded elevators. All right, but bigger picture. Don't worry about elevators here. Do you see the significant difference between these two problems? One is asking about a single individual from a population. One is asking about a group, a sample from a population. The math is the same. We use that normal CDF command both ways. It's just what numbers am I putting in? Specifically, what changes am I making to standard deviations? Because that's the one that changes. Okay, let's take a look at another example. All right. Well, actually, I don't have another example, but we'll take a look at how this is going to relate to what we're doing for the rest of the semester. So this is where we're going to introduce this idea of hypothesis testing. And in hypothesis testing, someone is going to make a claim about a population. And our job is to gather data and see whether that data supports that claim or not. So the claim that is going to be made about a population is going to be about a population parameter. Someone's going to claim what it is. And our job is to gather data to see if our sample data supports that population parameter. So I want to go back to an example from before to try to make some sense of this really quickly. And I'm going to go back to one that I've used many, many times. I'm going back to my can of Coke. I am going to claim 12 ounces is the mean amount of soda in my can. And if I assume that 12 ounces is true, then I should get a normal distribution where the mean should be about right there, 12 ounces, with some standard deviation that is acceptable based on the machine that I'm using to fill it. And let's say it's 0.05 ounces. Okay. All right, so I go out and I grab a sample from my population. And if I were to plot the mean from a sample, I should get something that should be relatively close to the middle. And if I got a sample mean that was relatively close to the middle, I would say, you know what? I feel good about that. I feel that the data is supporting that the average is about 12 or the average is 12. Now, what if I did it again and I got a value that was way over here somewhere? That's really far from the middle. Now I'm going to start to wonder and go, hey, should I have gotten that? What's the chance? What's the probability that I would get that value from a sample? And if the probability is sufficiently low enough, one could make an argument that maybe the machine isn't putting 12 ounces in. Or what if I did it again and I got something way out here? And if the probability of that amount of soda as a mean showing up in the cans was low enough, then I might be able to say, I don't think this machine is actually putting 12 ounces in a can, and that the claim of 12 ounces is actually wrong. Okay? So hypothesis testing is based on that logic right there. I need that space, so I'm going to delete it. But it's based on if someone makes a claim and the observed results have a very small probability of occurring, then we can conclude that the assumption is probably not correct. If I make a claim that something is true, you go gather data, and there's only a 0.5% chance that your data should have showed up how it did, I could then make the argument that, yeah, maybe my claim was wrong. Right. Let's look at some math here in this first example and see if we can make some sense out of it. Right. Assume that the population of human body temperatures has a mean of 98.6. So we're saying that we have an assumption here, a claim, that mean is 98.6 degrees Fahrenheit. Right? We're also going to assume that the population standard deviation is 0.62 degrees Fahrenheit. Right? If I were to create a sample of size 106, and I found that we got a sample mean of 98.2 degrees, what would that tell you? What information could I get from that? Right? All right. So I'm assuming normally distributed body temperatures with a mean of 98.6 degrees Fahrenheit and a standard deviation of 0.62 degrees Fahrenheit. If I create a sampling distribution of size 106, the mean of that sampling distribution is still going to be 98.6 degrees Fahrenheit, but the standard error of that mean is now going to be 0.62 divided by the square root of 106. And whatever that works out to be, don't really care. I'll put it in the calculator like that. Right? And then I'm supposed to figure out, well, if the middle's 98.6, what's the chance that 98.2 degrees Fahrenheit or lower, left tail, would show up? Now, if we assume that this claim is true, then a 98.2 or less should have a fairly high probability of happening. if that claim is false, or if we have reason to suggest that it might be false, then the 98.2 that we saw would show up with a small probability. So let's find that probability. What is the probability that our sample mean will be less than 98.2 degrees? I'm going to go to my calculator. I'm doing a normal distribution. I have no lower limit stated, so I'm just going to put in a big negative number. I have an upper limit stated of 98.2. I have a mean of 98.6, and I have a standard error on the mean of 0.62 divided by the square root of 106. I paste this back in. Now, before I flip over to the answer, I want to point out something. In the past, people have questioned, how can the lower limit be a negative number? You can't have a negative temperature. Shouldn't it be blah, 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 blah? Once you're beyond 3 standard deviations away from the mean, the horizontal asymptote comes into play. And so I'm putting in this stupidly large negative number, but I could use a much smaller negative number, or I could use even a smaller number, and you wouldn't even notice. Okay? And I get this. Okay, so what the heck does that mean? Well, first off, what is 1.552 times 10 to the negative 11th is how I interpret that. Scientific notation. So that means 0.1, 2, 3, 4, 5, 6, 7, 8, 9, 10 leading zeros, 1, 5, 5, 2. If you prefer it as a percent, so what does that tell me? Well, essentially that says that if 98.6 is a true mean human body temperature, I shouldn't have been able to get a sample with a mean of 98.2. It shouldn't have happened. It's a tens, hundreds, thousands, 10,000, 100,000, million, 10 million, 100 billion, 2 billionth of a percent chance of that occurring. So something is wrong here. Either I am the luckiest individual in the world when it comes to my random sampling of my 106 people, or the original claim that was made about 98.6 is not true. And that maybe we need to go back and revisit that. Now, does this prove that 98.6 is wrong? No, it doesn't prove anything. Does it give us a lot of strong evidence to suggest that 98.6 might be wrong? Yeah. Does the data support 98.6 being the mean body temperature? No, the data does not support 98.6 being the mean body temperature. And this is how hypothesis testing will work. So let's go back and start over. Someone is going to make an observation or an assumption or a claim about some particular thing. In this case, body temperature. We're going to gather data to test that assumption, that claim, that, in this case, body temperature. We're going to find the probability of our result or more extreme occurring. So when we calculated this probability right here, we found the probability of our result, 98.2 for a sample mean, or more extreme, colder, lower body temperature occurring. And if that probability is significantly small, we can most likely conclude that the original assumption for the problem was incorrect. Same thing would have happened if we would have gotten a really high number. Like if we were to say, okay, well, what was the probability that our sample, if our sample came back at, I don't know, 99 degrees, we would say, okay, well, 99 seems high. What's the chance that it would be 99 or higher? And then we could run that calculation. So the idea of this value or more extreme is if you're below the mean, more extreme will be a left tail. If you're above the mean, more extreme would be a right tail. Right. All right, last thing we have to take a look at in this is the idea of the correction for finite population. But we're already at 25 minutes, so I'm just going to tuck it in here at the end of this one, and it's going to make this kind of a long video. But this idea of sampling from a population up here assumes that your population is so big that 106 from it isn't really going to be a big deal. It isn't a significant sample size compared to the entire population. If you happen to have what's referred to as a finite population, or a population that is a relatively small population, it is possible mathematically that your sample size might be large enough to skew the results. And that anytime the sample size is more than 5% of the population size, then we have to do this correction by multiplying by the finite correction factor. So the standard error on the mean, SEM, standard error on the mean, that's our sigma sub x bar, right, has to be multiplied by that right there. Now, technically, it's always being multiplied by that, but when n is small compared to, when your sample size is small compared to your population size, this fraction right here is so close to 1 that it doesn't affect the results. It's only when your sample size gets big compared to the population that it ends up mattering, that ends up affecting it. Right? All right, so let's take a look at an example with a small population and a relatively large sample for that population. All right, so it is known that the population of white German Shepherds in the United States is about 4,000 dogs. I have no idea what a white German Shepherd is. I'm assuming it's a German Shepherd that is a white-colored German Shepherd. But we have a small population where N, capital N, our population size is 4,000. Right? And the mean weight for these is 75.45 pounds. Right? And we also know that they have a population standard deviation of 10.37 pounds. So this is all population data. Right? Suppose that we take a sample. Okay, so we're going to sample from this population, and we're going to take a sample of 225 dogs. So now n, lowercase n, is 225. Okay? Find the probability that the sample will have a mean that differs from the probability mean, population mean. Sorry, that's a typo. By less than 2 pounds. Find the probability that the sample mean, okay. So I'm going to create a sampling distribution where the mean of my sampling distribution is going to be that 75.45. And we want to find the probability that will differ from the population mean by less than 2 pounds. Differ by less than 2 pounds means it could be 2 pounds lighter, or it could be 2 pounds higher, but it can't be more. So we want to find the probability that it's in here, where this number is going to be 73.45 pounds. And this number is going to be 77.45 pounds. So that it doesn't differ by more than 2, and I want to find that probability there. Okay, I can do that. So it looks like I've got a lower limit, I've got an upper limit, I've got a mean. I just need a standard error on the mean. I need a standard deviation for the sampling distribution. Now the problem is this is relatively large compared to that. Right? Sorry about that. Our sample size compared to our population is more than 5%. So this would be a situation where I have to bring in the finite correction factor. So my sampling distribution standard deviation, which is normally just the standard deviation divided by the square root of the sample size, also has to get multiplied by the finite correction factor, which is that formula up there. Okay? So our standard deviation is now going to be 10.37 divided by the square root of 225 multiplied by the square root of 4,000 minus 225 divided by 4,000 minus 1. And that's going to be our standard error on the mean for this calculation. So now we've got everything we need. We've got a lower limit, we've got an upper limit, we've got a mean, we've got a standard error on the mean. I can calculate probability. So I go to my distribution menu, normal CDF, lower limit is 73.45, upper limit is 77.45, our mean is 75.45, and our standard deviation is going to be that whole mess right there. So 10.37 divided by the square root of 225 times another fraction, which is the square root of 4,000 minus 225 divided by 3,999. And I paste that all back in, and it's terrible, but I get, so to write it all out, make it look pretty, the probability that 73.45 is less than x bar is less than 77.45 is 0.9971, taking it to 4 decimal places, or about 99.71% chance. All right, so how do I interpret this? What does this tell me? Well, if I were to go out and grab a population, from the population of 4,000 white German Shepherds, a sample of 225 of them, to weigh each dog and find the average, the mean of those dogs' weights, I would have a 99.71% chance that the mean weight of that sample would fall between 73.45 and 77.45 pounds. This brings us to the end of section 6.4. Have a great day. I'll see you all back here for section 6.6.